we talked about multiplying matrices. All right, you take like rows times columns. So I've got two matrices up here. So 3 by 3 times a 3 by 3. First of all, can I multiply these two matrices together? Yes, we can. So remember, you always have to do that check real quick. You write the dimensions or the order of one matrix. You write the order of the second matrix. And then you check those inner dimensions. And if they match, then yes, we can multiply them together. All right, so I'd like you all to take a minute right now and multiply these matrices together and let me know what you get. By the way, what should the dimensions be of your final matrix? Nice, Jared, perfect. So those outer dimensions give you the dimensions of your solution matrix. All right, so go ahead, take a minute, multiply these. Remember, practice that skill, the rows times columns. And let me know what you get, just to kind of refresh our memories from class on Monday. Those ones and zeros make it pretty easy, doesn't it? All right, so you multiply like 4 times 1 plus 5 times 0 plus 2 times 0. You add those up, and that becomes the first number in your solution matrix. So maybe look back at those notes from last class, but this is where you take row times column, and we multiply all the corresponding elements together, meaning the first element of the row with the first element of the column, second with the second, third with the third. So when I'm taking 4 times 1, that gives me 4. And then we're adding the product of the other elements, plus 5 times 0, which is 0. And I'm going to add 2 times 0, which is 0. And that's just a 4. Sticking with the first row, we have to then multiply that times each of the subsequent columns as well. So we take that first row times the second column. We do that same process. So 4 times 0 is 0. Then I've got 5 times 1, which is 5, plus 2 times 0, the third element in each of those, which is 0. Add those up and we get 5. There's still one more column, so sticking with that first row, we multiply it by the third column, multiplying those corresponding elements. The first number in the row, which is a 4, gets multiplied with the first element in the column, which is a 0. 4 times 0 is 0, plus 5 times 0, which is 0, plus 2 times 1, which is 2. You add those up and you get a 2. Now that's the end of the first row, right? I've taken the first row and I multiplied it by every one of those 3 columns. At this point, then I jump down to the second row and repeat that process. Take that row times the first column, second column, and third column, and so forth. And I'd go down to the third row and multiply the third row times each of the 3 columns. Now, just looking at these the first 3 calculations I did, we had a 4 for the first one, 5 for the second, and a 2 for the third. Do those 3 numbers look familiar? Did anyone multiply the rest of this out and notice something funny about our answer matrix? What happened, Mia? It's the same thing, right? The entire matrix, right? When you multiply these out, we ended up getting this entire starting matrix was our answer. You get 3, -2, 1, 6, 4, -3. I had one matrix. I multiplied it by a completely different matrix, and I ended up getting the same thing. It didn't change a single element. They're all the same. Is that crazy? I wonder if this is a special property of matrices that we're going to use to solve equations later on in today's lesson. Could be. We'll come back to that. But isn't that kind of fun? Yes. Yes. Cool. All right. So here's the whole purpose of today's lesson. We're going to solve a matrix equation. Just like the name says, a matrix equation is simply an equation, meaning there's an equal sign on left side and a right side. But instead of just like numbers or variables, we now have matrices as each of the different terms or each of the different numbers. It's simply an equation of matrices. So this is learning target 3.3, the last one with matrices. And normally we're used to seeing equations written something like this, like 2x plus 3 equals 10, right? Isn't that normally the types of equations we solve with like numbers and a variable? Typically, we want to solve for the variable, right? We want to get that by itself. We're going to do the same thing, but just with matrices. Instead of individual numbers, I now have these collections of numbers, but the goal is still the same. We want to isolate the variable. But the only difference now is that variable, in this case I use the letter C, could be any letter, right? C, that variable that we're solving for, isn't just a single number, like x equals 2 or something like that. Instead, C is a matrix itself. So we're ultimately trying to figure out, all right, this first matrix, the -2, 5, 1, 0, if I took that matrix and I multiplied it by something else, then added the 8, 6, 2, 4 matrix, and I get this 15, -2, 6, and 3. We're trying to figure out what matrix could I plug in right there for C that would make this equation true, all right? So we could try guessing and checking. Wouldn't that be fun? Plug in every single possible combination of a 2x2 matrix in there to see what works? No, of course not. So we're ultimately going to be learning how we can solve for that matrix, all right? It's going to be a similar process, just like solving equations, we kind of undo operations to cancel stuff out. We're going to kind of do that same process. The only thing that's a little bit trickier is first off, like if I were to get rid of this 3, we would subtract a 3. Can I subtract matrices from each other? Are we allowed to subtract one matrix from another matrix? Remember our first learning target? Adding and subtracting matrices? We can do that, right? So I could subtract this matrix, from this matrix right there. We can do that. But the tricky part about these matrices is this step right here. To get that x by itself, we would normally divide by 2. With a matrix, though, I'd have to divide by this matrix right here. And unfortunately, we can't divide with matrices. So we have to use a different technique to cancel it out essentially. And that's what we're going to learn how to do next. All right, how do you cancel out a matrix that's being multiplied by another matrix? So here we go. In order to solve these matrix equations and figure out how to cancel out a matrix, we have to understand two special types of matrices. And they've got special names. We need to know about the identity matrix, and we need to know about something called an inverse matrix. So once we understand these two concepts, then we can go ahead and solve that matrix equation, because we need to use this concept of an identity matrix. We need to use an inverse matrix in order to solve these matrix equations. So that first type of matrix, the identity matrix, in parentheses, I just have a capital letter I. That's how we represent the identity matrix. The identity matrix is a square matrix. Now, what do you think I mean by a square matrix? It has to do with the dimensions. What do you think the dimensions have to be for a matrix to be considered square? Yeah, so Gavin said a 2 by 2, 3 by 3, 4 by 4. Basically, the rows and columns have to be the same. Just like a square, the sides are all the same. Exactly. So this concept of an identity matrix only exists for a square matrix, where the rows, or the number of rows, equals the number of columns. All right, so that's a square matrix. Basically, does that matrix look like a square? So it's pretty self-explanatory. And so only square matrices have an identity matrix. And this matrix is special because whenever you multiply the identity matrix times another matrix, your answer is that same matrix. It doesn't change it. Have we seen this happen yet today? Yeah, remember the warm-up? We multiplied by a matrix and it didn't change anything. That second matrix that we used with all like the ones and zeros, that was an identity matrix. Does that ever happen with like regular numbers? Sometimes if I had a number like 6, could I multiply 6 by a different number and still get a 6? Does that ever happen? Yeah, what number would I multiply by? A 1, right? We've done that before. So 1 is actually considered the identity number for multiplying, because when you multiply something by 1, it doesn't change it. Addition has an identity number as well. If I'm adding something, 6 plus what number still equals 6? A 0. Yeah, Alex. 0 is the identity for addition, right? If I add 0 to something, it doesn't change it. So this isn't a new concept of an identity. If you think about the word identity, isn't your identity just like who you are? It's yourself. So with an identity number, like a multiplying by 1, it doesn't change its value. It's still the same thing. It's still you, if you were a matrix, right? So the identity matrix, same idea. If I multiply something by the identity matrix, it doesn't change it. It's still itself. It's still the same identity. And so that's why I say it's similar to multiplying by 1 or adding 0. You don't change the value. It's still the same thing. So here are just two examples of identity matrices. Notice they're both square matrices, right? A 3 by 3 and a 2 by 2. And there's a collection of ones and zeros. Now the positions of the ones and zeros is very important. There is a pattern to it. What I want you to do is I want you right now in your notebook to create the 4 by 4 identity matrix. So try looking at these two matrices, see if you can figure out what that pattern is. Then I want you in your notebook to write down what you think the 4 by 4 identity matrix should look like. Where are all the ones and the zeros placed? There's a pattern to it. And each time the matrix gets bigger and bigger, the ones are still in a certain position, the zeros are in a different position. Can you see that pattern? Yes. So what do you think the 4x4 identity matrix will look like? Awesome. Yep. Perfect. So if you look at the 2x2, if you look at this diagonal on the 3x3, look at that diagonal. Notice that's where all the ones are. So that first diagonal from the upper left to the lower right is always going to be a 1. Everything else is a 0. I saw most of you had this, which was awesome. So basically 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. So this would be the 4x4 identity matrix. There's a single diagonal of 1s, and it must go from the upper left to the lower right. Then everything else is a 0. All right, now let's make a 25 by 25 identity matrix. Ready? No. You get the idea, right? Okay, so here's the first example of the day. I'd like you to multiply these two matrices together. All right, so remember rows and columns, rows and columns. So you have 1, 0, 0, 1 times 4, 6, 9, 2. Since these matrices are both 2 by 2s, yes, they can be multiplied together. There is a defined product. Now, if you look at that first matrix, hopefully you can recognize something. That 1, 0, 0, 1 is the identity matrix. So, if you ever recognize that when you're multiplying something by the identity matrix, it gives you 1, 0, 0, or one of them is that diagonal of 1s and everything else is the zeros, we know that multiplying by this is the same as taking a number and multiplying it by 1, meaning it doesn't change its value. So you can work this out, but it'll be just like that warm-up we did. So your first little shortcut is if you're multiplying two matrices and you recognize one of them is this identity matrix, guess what? You don't need to take the time multiplying rows and columns. I know that the answer is going to be 4, 6, 9, 2. If you did work it out, you would get that also, right? If I took 1 times 4 plus 0 times 9, that's 4 plus 0, and that gives me a 4 right there in the first spot. Do that for all 4 elements, and you're going to get the same thing. All right? So multiplying by this identity matrix doesn't change its value. We good so far? That first concept of an identity matrix. All right, so right here, it's kind of hard to see what I'm trying to get at here. One matrix times another matrix, does it equal the identity matrix? Well, if it does, what should we get when I multiply those two things together? Well, the 2 by 2 identity matrix is just the 1, 0, 0, 1. Right, so if you multiply them, do you think you get that? All right, let's see. So if we do rows times columns, I've got 1 times 0, 1 times 0, which is 0, plus 1 times 1, which is 1. All right, that's good. Now take the first row times the second column. Oh, fractions, so gross. But wait, they're easy fractions. We can work with 1/2. 1 times 1/2 is 1/2. 1 times negative 1/2 is negative 1/2. Add those up and we get a 0. So far, is it looking like the identity matrix? Yep. Go to the second row. 2, 0 times 0, 1. Well, 2 times 0 is 0, plus 0 times 1, which is also 0. That equals 0. Still good. And finally, take the second row times the second column. And we've got 2 times 1/2. Well, 2 times 1/2, that's just going to be a 1, right? Half of 2 is 1. Plus 0 times negative 1/2 is 0, and that gives us 1. If we put these in a matrix form, you see we've got 1, 0, 0, 1. Is that the identity matrix? It is. So why'd I have you bother multiplying these two crazy matrices together? Well, I want to show you that if you multiply certain matrices together, they can turn in to this identity matrix. And then if I multiply something else by the identity matrix, I can pretty much ignore this, right? If I multiply something by this identity matrix, I basically cross this off because it doesn't do anything to my problem. And that's the same principle we're going to use to solve matrix equations. Just like if I have 2 times x and I'm solving for x, I divide by 2 because 2 divided by 2 is 1. And do we bother multiplying anything by 1 or do we just cross it off? Just cross it off. So that's kind of the same concept here. If I multiply a matrix by a certain other matrix, it turns into this identity, which we can just pretty much ignore. And that's what we're going to have to do. That's how we're going to be like canceling things out with matrix equations. So all we have to do then is figure out, all right, how do I find this magical second matrix that will cancel out my first one and turn it into the identity? How do we do that? Well, let's think about a basic concept with numbers. 5 times what number equals 1? Any ideas? 1/5. Right? If you take 5 times 1/5, essentially the 5s cancel out and you're left with the 1. Awesome. How about 2/3? Do you remember that trick? How do you cancel out a fraction? You just like flip it. 3/2. And here, essentially, the 2's would cancel, 1 on top, 1 on bottom. The 3's cancel, 1 on top, 1 on bottom. We're left with a 1. Do you remember what that's called when you flip the fraction upside down? Reciprocal. Remember me using that term earlier this year when we were solving certain equations with fractions? You multiply by the reciprocal, and it basically cancels out that first term. Well, to cancel out a matrix, we're going to multiply by its reciprocal in a way, but it's not called a reciprocal. It's called an inverse matrix, all right? So this is the tool we're going to use to try to cancel out a matrix. And this is the second thing that we needed to learn about in order to solve matrix equations. So an inverse matrix. It's also a square matrix, just like the identity, right? So the rows and columns have to be equivalent. So number of rows has to equal the number of columns. And it's a special matrix because when you multiply it with another matrix, you get the identity, that 1, 0, 0, 1. Remember, that identity matrix, you can essentially cross off. You can ignore it. It doesn't change anything if you multiply by that identity matrix. So that's kind of our goal. I want to change a matrix. If I want to cancel it out, what can I multiply it by to turn it into the identity matrix so I can just cancel it out and ignore it? So this concept, same thing as like multiplying by a reciprocal with just numbers. If you multiply by a reciprocal, it cancels out and you can ignore that coefficient, whatever was in front of our variable. Now, every square matrix does have a different, unique inverse matrix. Unfortunately, it's not as easy as just 1, 0, 0, 1 for the identity. The inverse matrix is going to be different based on that first matrix. Just like every number has a different reciprocal don't they? Every fraction has its own unique reciprocal. Every square matrix has a unique inverse. And the weird thing is some matrices don't even have an inverse. What? Which is weird because like this doesn't happen with numbers. Or does it? All right, I'm getting too deep for algebra 2. I'm sorry. I'll stop. All right, are we kind of understanding the concept so far, like where we're going with this and building up to solving it, or about the identity or this inverse so far? We're going to show this in action. But please, if you're totally confuzzled, let me know. So here's the concept. First off, I don't know if you saw in the previous slide, right here in the parentheses, that's the M, that's just whatever we name our matrix. Remember, we always use capital letters for a matrix. But there's this -1 for an exponent, and that's read as inverse, okay? It's not M to the negative first power, that's M inverse. So on this slide, I'm just showing you, if I take any matrix M and I multiply it by M inverse, the result will always be the identity matrix. Any matrix times its inverse equals the identity. Which again, in terms of solving an equation, if I've got this identity matrix in there, I can just cross it off. I can pretty much ignore it because it doesn't change my value. And again, so that's our goal. If I have matrix M in an equation and I want to cancel out matrix M, all I have to do is multiply it by M inverse. And then I would essentially just like cross those off. M times M inverse cancels out. It's like multiplying 5 times 1/5. You cross them out. Or 2/3 times 3/2. You cross them out. They cancel. And so we're going to use this concept to solve the matrix equations, because we're going to use the inverse to cancel out an entire matrix. It's not just a single number though, because it's this grid of numbers that we have to figure out how to cancel. How do we calculate the inverse matrix? All right, so here's the first bit of real learning for today. We're going to do some calculations now. Turns out you already know a little bit about how to calculate the inverse. There's two parts to it. The first thing we need to know is the determinant of the matrix. That word sounds a little familiar. When did you see determinants already this year? Cramer's rule. Yes, excellent. Remember Cramer's rule? You've got those different like 2x2 grids, and you just kind of do like crisscross. You like multiply one diagonal, multiply the other diagonal, and subtract them. That was called a determinant. We had like the coefficient determinant, and then the x determinant and the y determinant. Those are determinants. Well, matrices also have a determinant, and it's by doing the exact same thing. So this determinant is a number associated with each matrix, and it's calculated by simply doing this exact same process that you see down here. Right? When you take a 2x2 grid, back when we learned Cramer's rule, you didn't know that that was actually a matrix, right? I just didn't use that terminology yet, but that's all it is, this 2x2 grid. And so remember, to calculate a determinant, you take one diagonal, A times D, and that's right here, and you subtract. That's the really important part. Most students on using Cramer's rule in the last test, they forgot to subtract those two diagonals. All right, so make sure you put that minus sign. Then you take the second diagonal, B times C. And that's just going to be a single number, right? A times D is one number. You subtract the product of another number, and boom. That is the determinant of that matrix. For Cramer's rule, we found the determinant of the coefficient matrix, essentially. And so make sure you familiarize yourself with this process. All right, hopefully it's still in there from Cramer's rule. This shouldn't be something new. You've practiced this a little bit already. And just a quick note on notation. If you see a group of numbers where there's the little like feet on the end of those lines, that's referring to that matrix, right? That's not saying calculate something. That's just the matrix itself. However, if you see just these vertical bars, this actually is an operation. This is actually telling you, hey, don't just look at these numbers, calculate the determinant. It's like the difference of me just on a test, just putting the number 4 on there, you don't do anything with it, versus if I put 4 times 5, you would know, oh, Mr. Wojcik wants me to multiply these numbers together. Same concept. On the left, this is just a matrix. You don't do anything with it. It's just there. But on the right, if you see just those vertical bars without those like little feet on the ends of it to kind of cap it off or go on the bottom, that's actually saying, hey, I want you to calculate something right now. It's as if I'm giving you an operation saying, hey, perform this operation on these numbers, okay? So like example 3 down there, 5743, even though I don't have any words saying, hey, calculate something, you should recognize, oh, these are just vertical bars. I'm supposed to calculate the determinant, right? Because I don't see those little like feet on the top and the bottom. So everyone go ahead right now on example 3 and calculate the determinant of 5743. Remember, it's just that simple: crisscross applesauce. I had to. Okay, hopefully this is a relatively quick calculation. So whenever you see just vertical bars around this matrix of numbers, we always take the first diagonal, and remember to always start in the upper left corner. The same way you would start if you were reading a book. You start in the upper left corner, right? And you take 5 times 3, which is 15, and then put the minus sign right away. I can't stress this enough. I want you to get in the habit of, as soon as you write that first number, put the minus sign. Otherwise, chances are you're going to mess up the next part. It happens all the time. Now multiply the second diagonal, 4 times 7, which is 28. Now we subtract these two numbers, and we get negative 13. Anyone else get negative 13? Wonderful, wonderful. Okay, so calculating the determinant is the first part of finding the inverse of a matrix. And guess what? This is the hardest part of finding an inverse matrix. But isn't that pretty easy to do? Like the math involved is base level, right? So that's the only real calculation part. The next part is just kind of, oh, I'm sorry, I have one more example for you. Go ahead and try one more. Just to make sure we've got this down, because you need to calculate the determinant if you're going to find the inverse. But I threw in some negative numbers to try to trip you up. Are you going to mess up, Gavin? You sure? Ooh, pretty confident. I hope you remember to subtract. But there's so many negatives. It's so easy to mess up. Hey, negatives can be tricky. Right? Jared's got it, though. Hey, real quick, check, see if you guys got the same thing. Oh, you guys are so smart. Always known that about you two. Make sure you start with the first diagonal, not the second diagonal. Negative 2 times negative 5 is positive 10 minus. Put the minus right away, please. Then take the second diagonal, multiply them. Negative 3 times negative 1 is positive 3 and 7. What? Yes? No? Yes? Is it? Yes? Okay, it's 7. All right, some of you are messing with me. All right, so that's how you calculate the determinant. Hopefully we're all golden with that process. Oh, this part's a little scary. Oof. So remember, we can find the inverse for any square matrix, not just 2 by 2s. We could do it for a 3 by 3, or a 4 by 4, or a 25 by 25. The determinant of a 3 by 3 matrix is called a third order determinant. So this right here is going to be the main reason that I want you to get or have access to a graphing calculator, because there is a way to do this by hand, but it's a little involved. And I am going to show you this process by hand. Just like I said, I'll teach you how to do everything without the graphing calculator, but it would be easier if you had one, because then it's just a single button press. Now I'm going to show you just the general formula first for a 3 by 3 determinant, and then we're going to do an actual example with real numbers, and then we're going to try to put this out of our mind because it's crazy. So like on a test, I'm not going to have you calculate one of these by hand, but if you don't have a graphing calculator, you might have to, but it's not like a skill that I'm going to assess, but I do want to show it to you. I mean, we just have to laugh a little bit. All right, so if you have a 3 by 3 matrix, you want to find its determinant. There also is a unique number associated with it since it's a square matrix. So just go ahead and memorize this formula for me real quick, and then we'll move on to an example, okay? It looks ridiculous, but there is a system. Let me make this a little bigger. This is called expansion by minors. You might hear that in a future math class, and I want your teacher next year to be like, didn't Wojcik teach you expansion by minors? And that's not minors as in you're under 18. It's also not minors as in, you know, we're digging up coal in the mines, like the Seven Dwarfs. But they mine diamonds. I mean, what a cool job. What do you do? Oh, I go digging for diamonds every day. So it's this insane combination formula. Now, that's not actually a number yet in itself. If you look at it, it's A, which is a number, right? That's our first element. But then what do these vertical bars here indicate around those 4 numbers? To calculate the determinants. And you have to calculate that determinant. You have to do that 3 times, right? For each of those groupings. But how in the world are you going to memorize all of those groupings? That's insane, Wojcik. Come on. Don't worry. There's a method. In order to calculate this determinant for a 3 by 3 or anything larger, take a look at this. Start with the first element. I want you to circle it. Circle that first number, and you write that number down, okay? So you start with that first element, right? Now, going back to the 3 by 3, watch this. I'm going to cross off the rest of the column and the rest of that row, and look at the 4 numbers that I'm left with. Do you see this E, F, H, I? Well, check it out. E, F, H, I. So whenever you circle a number, ignore everything else in that row and column, and the 4 numbers you're left with, you then take the determinant of those 4 remaining ones. Then, to get the next number, you move over 1 point in the row. So now I'm going to go over to the B. All right, and I write B here. And if I cross off the remaining row and column, so cross off the rest of row B, cross out column B, look at the 4 numbers that I did not cross out. See the D, F, G, H? Well, it's right there. D, F, or I'm sorry, G, I. D, F, G, I. You then do this a third time. Circle that last element, C. Start with the C. Cross off the rest of the row, the rest of that column, and look what we're left with. These 4 elements, D, E, G, H, and that's right here, D, E, G, H. Once it's written like that, pretty easy. These are just basic determinants, right? Where you do the crisscross, multiply, subtract. Yes, sir? Wonderful question. Why is there subtraction there? So this is a little weird. Matrices are crazy. Sorry about that. Every element in a matrix is associated with a specific sign, either a positive or a negative sign, behind the scenes, but you don't really see it. Turns out that it always starts off with a positive, and then this pattern will alternate between a positive, negative, positive, negative. So plus, minus, plus, and the same thing is true for each subsequent row. We still continue to alternate. Middle row would be minus, plus, minus, then plus, minus, plus. So this is a secret behind the scenes overlay to a matrix. If you're calculating the determinant, you add, so just looking at the top row here, you would add this first element, whatever it is. Now remember, if A is a negative number, you would keep the negative sign. It's saying you add whatever that number is. Whatever B is, you subtract it. Okay, so if B is 3, you would write over here minus 3. But if B is negative, you'd have the double negative thing and it would turn into a positive. Super confusing, I know. And then whatever C is, you would add it. Now, each subsequent row also follows a similar pattern. Now, why would you need to do that? Well, just for this example, I showed you how to do this with the first row. But to find the determinant of a 3 by 3, you can do it with any row. I could do it with the second row or with the third row if I wanted. So I could also do the same thing. If I started with like the D, I could cross off the rest of that row and the rest of that column and see how I'm still left with 4 numbers. So I could do the same thing. I could calculate the same determinant by doing D times B, C, H, I. But since I'm in row 2, you have to make it negative, because that behind the scenes pattern says that it's negative, positive, negative for these. Just like for this first row, I have a plus, minus, plus. If I'm using row 2 to calculate the determinant, you would do minus, plus, minus, and so forth. Seems crazy, right? What's kind of cool is this pattern is for any size matrix. So you've actually already used that with the 2 by 2 matrix. A 2 by 2 has plus, minus, minus, plus. Remember how when you do your crisscross, you always subtract that second number? That's because of this right here. Right? Because you add the first row, but you subtract the second number because of this minus sign right there. That's why you always subtract that second number in your 2 by 2 determinant, because this pattern is still there behind the scenes. If it were a 4 by 4, that alternating pattern would continue. Every row, every column is swapping to make this almost like a checkerboard with pluses and minuses. Great question, Gavin. I know. Yeah, sorry. Yay. Okay, let's actually calculate one. Just because we got time, right? We have time to calculate a 3 by 3 determinant. Let's do it. It's good practice. So first, we have to write down this matrix. 1, 5, 4, 9, 3, 6, 7, 2, 8. So we need to calculate the 3 by 3 determinant. So I'm going to walk you through this process, just make sure we're on the same page. Now, to calculate a determinant, you can choose to do any row, but for the most part, you'll probably just stick with the first row. The only reason I would ever choose like the second or the third row would be if there's a 0 in it, because you'd always take 0 times everything else. You can just ignore that whole piece, but there are no zeros here, so we're going to just start with the first row. We circle the first number, which is a 1, and we write that number down, 1. Now, cross off everything else in the same row and column as that 1. And we're left with 4 numbers. Those 4 numbers we're going to write next to the 1 as a determinant. So it's 1 times the determinant of those 4 numbers, which we'll do in the next step. Right? Let me just write out the whole first line. Now go back to our matrix and circle the second number, the 5. Now I'm not going to write a plus 5 because we always have to subtract the next term. So we added that first term. I'm going to write minus 5 because of that alternating pattern scheme. Cross off everything else in that row and everything else in that column, and we're left with 4 numbers. We're going to write those as a determinant. 9, 6, 7, 8. All right, one more. Circle the 4. Now this is back to a positive. We're going to add this value. So I'm going to write plus 4. Cross out the rest of that row and the rest of the column, and we're left with 4 numbers. We write those 4 numbers, 9, 3, 7, 2. All right. This is looking easier by the, no. The calculations aren't difficult, it's just a lot to remember. So now what we need to do for each of these groupings is calculate that crisscross determinant. All right, so this first piece says take 1 times the determinant. So that determinant, we take 3 times 8, which is 24. So I'm going to write 24. And look how I'm doing this. I'm keeping the number out in front, then putting a parentheses for the determinant, because I had to calculate the determinant first before I multiply. Minus the other diagonal, which is 2 times 6, that gives me 12. And again, we'll subtract those in the next step. Minus 5 parentheses, that was the number out in front of the 2 by 2 matrix. Do not distribute it in. You cannot distribute into a determinant because of order of operations. Says you have to find the determinant first, basically. Parentheses comes before multiplication. And you take 9 times 8, which is 72, minus 7 times 6, which is, yes. For some reason, students always forget that one. 7 times 6. And then that last piece, plus 4, times the first diagonal, 9 times 2, which is 18, times 7 times 3, which is 21. All right, this isn't looking as scary anymore. There's a lot of numbers, but those are some basic operations that you've been able to do for like 10 years. All right, let's do some subtraction. So this is 1 times 12 minus 5 times 30 plus 4 times negative 3. All right, this is looking nicer. 1 times 12 is 12. 5 times 30, is negative 150. 4 times 3 is negative 12. So close. You got it? Whoa, nice job, man. Well, I mean, it's adding and multiplying, so don't pat yourself too much, but good job. A lot of steps. And then here, if I have a positive 12 and a negative 12, that equals 0 if I just combine those first. And what we're left with is negative 150. Woo, we did it. We calculated a 3 by 3 determinant. Only took us 12 minutes. Isn't that fun? Yeah, it's so good. Yeah, oh boy, yeah. So you can do this by hand, or you can use a graphing calculator and get it right away. So, oh, and I bet a lot of you are wondering, hey, can we do it for a 4 by 4? No. Just to give you an idea of how disgusting that would be, you'd basically take the number, cross out the row and column, but then you're left with a 3 by 3 determinant, and you have to do that again. The row and column, you're left with the 2 by 2 determinant, but you have to do it for every element in there. So it gets pretty gross pretty quickly when you get one dimension bigger. We're not going to even touch that, all right? Good job. Okay. Oh, yeah, back to inverse matrices. That was enough with determinants. We're going to pretty much stick with 2 by 2 determinants, if that's okay with everybody. Just the crisscross. Are we okay with that? Or does anyone really want to do more 3 by 3s? Just raise your hand if you want me to do some more. And 1 by 1. It's true. 1 by 1 determinant. It's just itself. Okay. So here is what we were trying to get. If this is matrix M with these 4 elements, A, B, C, D, and we want to find M inverse, okay, how do I calculate the inverse matrix? There are 2 parts to it. First, there's going to be a fraction out in front, 1 over AD minus BC. And I put my little dude there helping me out, saying, hey, look, it's the determinant, right? A times D minus B times C is that crisscross applesauce. So this first part is really the reciprocal of the determinant. You take 1 over the determinant, all right, for this inverse. All right, get out of here, dude. So it's 1 over, I'm just going to abbreviate the determinant with DET. Okay, that's not something new then. Some of you might see, oh, I have to memorize some other weird combination of letters and numbers. Nope, you don't. You already know how to do that really easily. You take 1 over the determinant, and then you multiply it by a certain matrix. Now that matrix has those same 4 elements that we started with, but we have to kind of change it up. And here's what we're doing. If you notice that first diagonal, what we're doing here is swapping the first element with the last element. So notice here's A and D in their initial positions. Here in this matrix, they've been swapped. So your first step is take the last element and put it in the beginning, take the first element and put it at the end, all right? Then that other diagonal, you don't swap the numbers positions, you just change the sign of them. So if you notice right here, there's just a negative sign in front of them, but they stay put, right? B stays in the second spot, C stays in the third spot, you just flip the sign. Now, keep in mind that that negative doesn't mean you just make it into a negative number, because if it were negative already, you'd have like a double negative and it would switch to a positive. So think of that negative sign as being, so you keep B and C in place, but whatever it was, you change the sign. If it were positive, it becomes negative. If it were negative, it becomes positive. So that's the easier part. You don't have to actually calculate anything. The only calculation for an inverse is this determinant part, which you're all really, really good at. One diagonal minus the second diagonal. All right, let's practice this. So here's a 2 by 2 matrix. Go ahead and jot this down. 3, 2, 4, -2. And our job is to calculate B inverse. So there are two parts to it. First, we just want to calculate the determinant, right? We need to use that determinant. And so I'm going to do that right off the bat. 3, 2, 4, -2. To calculate the determinant, remember, we just take that first diagonal. We multiply 3 times -2, which is -6, minus, then multiply the numbers in that second diagonal. 4 times 2, which is 8. That gives us a -14. Did you get -14, Gavin? So that's the determinant. So to calculate B inverse, B with that little -1 for an exponent, we start by writing 1 over -14, 1 over the determinant. All right, that's the first little part. Then it's going to get multiplied by this rearranged matrix. In this new matrix, this 2 by 2 that we're going to multiply with, it's going to have those same 4 elements that we started with up in B. But we just have to do a few little changes, little tweaks. First thing we're doing is switching the positions of the first element and the last element. Don't change their signs, just swap their positions. So -2 is now going to be up in that first spot. The 3 is going to be in that last position. The other two numbers stay put. So the 2 is still in the upper right, the 4 is in the lower left, but we just have to change their signs. They're both positive numbers, so I'm going to make them both negative numbers. So that's now a -2 in the upper right and a -4 in the lower left. And that's it. That's the inverse matrix. Now, when we are using this to solve a matrix equation, generally we're going to leave it with these two parts, with this fraction out in front and the matrix inside. But if you think about it, this fraction in front, that's kind of like scalar multiplication. Do you remember when we had like a number in front of a matrix and we distribute it inside to every element? Technically, we would do that here. Now, I know you're thinking fraction, that's gross, but this will always have a 1 on top, which means there isn't actually any multiplication going on. Whatever's on the bottom, like this is divided by -14, we just do that to every single element inside the matrix. So if I wanted to take this one step further and write it as an actual 2 by 2 matrix without anything in the front, I could just divide every one of these numbers by -14. Right? As if I took this scalar number in front and just multiplied it in. And then each of those fractions, you would just simplify them if you can, right? Like -2 over -14 would be 1/7. This is also 1/7. Down there, that'd be 2/7. And this one you can't simplify, so it's -3/14. So technically, this is the official inverse matrix, right? It's a 2 by 2 matrix. It's a square matrix. There's nothing out in front. When you calculate inverse matrices on your Delta Math tonight, this is how it's going to want you to type it in as a single matrix. So all you do is distribute that number in. When you're solving equations, though, it's going to be a lot easier to leave this fraction out in front, which I'll get to to that in a moment. But that's your inverse matrix. 1 over the determinant, and then you just switch those numbers around a little bit inside the 2 by 2. And that's B inverse. Whew, we're doing great. I know this is all completely brand new. Your minds are probably blown. But we still haven't solved a matrix equation yet. I'm sorry, I don't mean to laugh, but whew, we're getting somewhere. We've got all the pieces now. Let's practice this again, though. I want all of you to calculate the inverse of this matrix on your own, please. So remember, there's 2 parts. It's 1 over the determinant. Let me make this a little bigger for you. Applesauce. So it's 1 over the determinant. And then you make that square matrix with those same 4 elements, but you just kind of tweak them a little bit. All right. All right, I like what I'm seeing. Yeah. Good. Awesome. Yes. Yeah. This is great. We're catching on. Oh, very cool. All right, so a lot of you, you're doing it great. Awesome. Very, very proud of you. We take the first diagonal, 3 times 1, which is 3, minus, always put that minus sign right away, -6 times 4. So here's why I always urge you to put that minus sign first, because this is a -6 times 4, which equals a -24. And right there, you see we've got the double negatives. It's going to switch to a positive. So this actually is going to be a positive 27 is the determinant. So for the inverse matrix, we'd write 1 over the determinant, 1 over 27. We make the grid again. And I take the first and the last element, the 3 and the 1, and you switch their positions. So 1 is going to be first, and 3 is going to be last. The 4 and the -6 stay put, but you switch the signs of those numbers. So that 4 becomes a -4. And here, the -6, that's going to actually switch to a +6 because it's like a negative of a -6. And those 2 negatives make it a positive. So again, you could stop right here. If you're actually solving a matrix equation, you're going to want to save that division step for last. But if I'm just asking you for an inverse, go ahead and distribute that inside the parentheses to get a single square matrix. So it'll be 1 over 27. negative 4 over 27, 6 over 27, and 3 over 27. Those two on the bottom can both be simplified further because the numerators and denominators are both divisible by 3. Oops. So my final matrix will be 1 over 27, negative 4 over 27. But here, if I divide both of those by 3, we're going to get 2 over 9. Divide both of these by 3, we get 1 over 9. So right there in green, that would be the official simplified inverse matrix. But still what I have in red, technically that represents the inverse matrix as well, that we're going to be using to solve equations, which we're just about to actually get to. Oh my gosh. I'm glad we had a block day for this lesson. You're doing amazing, everyone, by the way. I know how tough this has got to be. Just getting your minds blown up with math all in one day. But don't worry, we're going to slow down for the next week. First, any questions on this inverse matrix? Did anyone have that, by the way? Just a quick show of hands or a thumb up or something, or a nod. Let me know, like, yeah, you're catching on. Okay. Any questions? Clarifications? I don't want to go too fast. Okay. All right, for this one, I think you're pretty good at this already. We know we do that determinant. And so that's 20 minus 4 times 5, which is also 20. You subtract those, you get a 0. Now to calculate the inverse matrix, you always write 1 over the determinant. 1 over 0 in this case. Then I've got my fancy matrix, 2, negative 5, negative 4, 10. However, I don't need to actually do anything further. I don't need to even write that second matrix because of this right here. If you calculate the determinant of a matrix and you get a 0, well, this part right here, 1 divided by 0. In mathematics, are we able to divide by 0? You can't. Here's the reason. If I gave you a sheet of paper and I said, hey, I want you to rip this up into 0 pieces, could you do it? No, if you have one sheet of paper and you shred it up, then you'll have 2 sheets of paper, right? You'll have 2 pieces. You shred those up, you'll have 4 pieces. So if I give you a thing, you can't make it into nothing, right? You can't divide it. You can't divide something by 0. You can't divide something or break something up into 0 pieces. There's always going to be at least 1 piece. So because of this, determinant being 0, this is the only time that you will not have a determinant, or the determinant is 0, but that means you will not have an inverse matrix. So this inverse matrix does not exist. All right, there is no inverse matrix when the determinant is 0. Sometimes that happens. Only when the determinant is 0, okay? So if you do the crisscross applesauce, you get a 0, just stop right there. There's no inverse. That was an easy one. What does this have to do with equations? Okay, with the last 15 minutes of class, let's finally get to the learning target. Don't write this. You don't need to write this down. This is kind of what I talked about earlier in the class. So we're solving a matrix equation just like we'd solve a regular equation, right? We want to isolate the variable. And we have to do different operations. You have to cancel out certain operations. The opposite of adding a matrix, we would subtract a matrix. The opposite of subtraction is addition. But the one thing that's tricky is, what if 2 matrices are being multiplied? You have to undo multiplication. With numbers, you would just divide to do the opposite of multiplication. But we can't do that with the matrix. So instead, if 2 matrices are being multiplied, whichever one we want to cancel out, we would multiply that matrix by its inverse. Because multiplying a matrix by its inverse cancels it out, because it turns it into that identity matrix, which we can just ignore. So that's going to be our process. To cancel out a matrix, we have to use that inverse matrix. So we have to figure out that inverse matrix, and then we multiply by it. So let's practice. Go ahead and write this equation down. This is a matrix equation now. So 3x2 matrix equals M minus another 3x2 matrix. And your task is to solve for matrix M. So some matrix minus the one on the right equals the one on the left. What is that matrix M? We want to get the variable by itself. Right now, M is on the right side. You leave it there, leave it on the right side, but you want to cancel out everything else on the right side by doing those opposite operations. You want to cancel things out. So on the right side here, we've got this -1, 2, 7, -9, 1, and 12. See how this matrix is being subtracted from M? If I want to cancel it out, what would the opposite operation be? Addition. So if I add this exact matrix right here, well, any matrix, minus itself or a negative matrix plus itself would equal 0. And it would cancel out on this side. Just like if I had a -3 and I added 3, we'd cross it off. But since it's an equation, if I add something to one side of the equation, what do I have to do? Add it to the left side, right? That's where our actual calculation is going to come in. So if I added this matrix to the right side to cancel out, to keep things balanced, I have to add that exact same matrix to the left side. So I'm going to add this -1, 2, 7, -9, 1, 12. So if I add those two together on the left, that'll equal, well, the right side, after things canceled out, we'd be left with just M. So that will be my answer. That'll be matrix M. Adding matrices, remember, you just add the corresponding elements. The first with the first, second with the second, and so forth. Should be pretty easy for everybody. If I add those up, I don't have a lot of room because matrices are huge. So here's what we're going to get. 2 plus a -1 is 1. 9 plus 2 is 11. -6 plus 7 is 1. 7 plus -9 is -2. 1 plus 1 is 2. 0 plus 12 is 12. So when I add those two matrices together, this is the new one I get. And this equals matrix M. You solved a matrix equation, finally. It only took us 85 minutes to get there, but we did it. Are you okay with this? Like opposite operations, right? Add or subtract. That's the basic part. Okay, here, let's go ahead and jot this down. It's a 1x3 matrix, -4, 25, 30 equals 3b. So that's 3 times matrix B. Now that would be considered scalar multiplication, right? 3 times whatever that matrix B is, but we're still solving for B. Plus the 1x3 matrix, 11, -2, and 9. Our goal is to isolate matrix B. I want to get that by itself on the right side. But there are two other things on the same side. There's the 3 in front of it, and then there's this other matrix that's being added to it. Which do you think I should cancel out first? The 3 or the matrix? The matrix. Why? because it's being added, right? You always cancel out whatever's being added or subtracted first, just like a regular equation. So we're going to subtract this matrix, which will cancel it out because it'll equal 0, which doesn't do anything. But then I have to do that same operation on the left side. So I'm going to subtract this 11, negative 2, 9. You just subtract corresponding parts, but please be careful with subtraction. Remember, you're subtracting every element in that second matrix, so be careful with those negatives. Negative 4 minus 11 is negative 15. 25 minus a negative 2 is actually like 25 plus 2, which gives us 27. 30 minus 9, 21. Equals 3 times matrix B. Now we're still trying to get B by itself. What is that matrix? But it's being multiplied by 3. Now 3 isn't a matrix, it's just a scalar quantity. It's just a single number. So can I just divide by 3? Yes, we can. I don't need to do the whole inverse thing. To cancel out the 3, we can just divide by 3. Now we'd have to do that to every element on the other side. So just divide each element in that matrix on the left by 3. Once you do that, we'd get a negative 5, 9, 7 equals matrix B. Da 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 da. You solved another matrix equation. Good job. But these were the easy ones. So now what happens when two matrices are being multiplied? Let's go ahead and write this down. And now we're going to have to use an inverse. Because on the left side, we're solving for matrix Z. And Z is being multiplied by another matrix. That negative 2, 5, 1, 0. I need to cancel that matrix out. If it were a number, I could just divide by that matrix, but that's not an operation that we have available to us. So here's the idea. So just if we represent this with letters, essentially like matrix Z times matrix Y equals matrix X. And I want to get matrix Z by itself. So to cancel out that Y, let me leave a little more room. To cancel out matrix Y, what we need to do is multiply Y by its inverse, right? Because Y times Y inverse will cancel out and leave me with just matrix Z by itself, right? When I multiply these two. But if I multiply the left side by Y inverse, guess what? The right side, right? You always do that same operation. So X needs to be multiplied by Y inverse, okay? Now this on the right, that's what our actual calculation is going to be. On the left, do I need to take the time multiplying the rows and columns with Y and Y inverse? We know that's going to cancel out, right? It'll equal the identity matrix, which then we just ignore. So essentially, we just cross those off, and Z equals X times whatever Y inverse is. So we need to figure out what Y inverse is and multiply it. One quick note. When you multiply matrices, this is crazy. The left and right order of the matrices does matter. It's not like numbers where you can flip the sides. It's not commutative. And so if I'm multiplying matrix Y by Y inverse and Y inverse is on the right side, please make sure that it's also on the right side of the matrix on the other side of the equation also. And I'll focus more on that next week. But let's go ahead and calculate this. So I need to find the inverse of this matrix. All right, that shouldn't be too bad. We're good at finding inverse matrices. It's 1 over the determinant. So what is the determinant of this matrix? Oh, look, man, I give you a nice easy one, didn't I? 0 minus 5, it's negative 5. Now we need to just do that little rearranging of the terms inside of this matrix. So the negative 2 and the 0 switch positions. The 5 and the 1 stay put, but you switch their signs. This is a negative 5. This is a negative 1. So this is the inverse matrix. If I took this whole piece and multiplied it by this guy, they would cancel out. Now, we don't need to take the time right now to actually multiply them together. We know they're going to cancel out, so don't waste your time. The calculation we need to do is taking this inverse matrix, and we need to multiply it over here on the right side, because if I multiply the left side by that matrix, I have to multiply the right side by that matrix. So times 1 over negative 5, 0, negative 5, negative 1, negative 2. Now you could distribute that negative 1/5 into the problem, but then you're going to have fractions, and I don't want you to multiply matrices with fractions. That gets crazy. So because the negative 1/5 is a scalar quantity, we are allowed to move this out in front. And so the actual calculations that we're doing is going to be just multiplying those two matrices on the right. So here's the work we have to do. We have to take negative 10, 40, 0, and positive 10 times 0, negative 5, negative 1, negative 2. We're going to multiply those together first. Once we're done, then we'll go ahead and then divide by that negative 5 as our last step. But we want to multiply the matrices together first. It makes it a lot easier. So this is our calculation. This represents matrix Z, right? That's where our goal was, to determine what is Z. We're solving for matrix Z. So I'm multiplying those two 2x2 matrices. That's just the whole rows and columns, rows and columns. So when I take the first row times the first column, 10 times 0 is 0. 40 times negative 1 is negative 40. This gives me negative 40 for my first element. Then I take the first row times the second column. Negative 10 times negative 5 is 50. 40 times a negative 2 is negative 20. That gives us 30. Then drop down to the second row times the first column. 0 times 0 is 0. 10 times negative 1 is negative 10. Our third element is a negative 10. Second row times second column. 0 times negative 5 is 0. 10 times negative 2 is negative 20. That gives us negative 20. So that was just matrix multiplication, just like we did earlier this week. So I'm going to write those in my matrix here. So we have a negative 40, 30, negative 10, negative 20. All right, we're super close to the end now. What's the one last piece that I need to put in there? So that 1 over the determinant piece, negative 1/5, is still in front. Now, it's going to be nicer to distribute that in, because look at, don't these numbers all divide nicely by 5 also? As opposed to if we put that 5 in the matrix first, you'd have like 1/5 and 2/5. You're going to be trying to do all that calculation with on the right, which would just be gross. So when you're solving the matrix equations, keep that number out in front until the very last step right here. So now I'm just going to divide every term by -5. So that's going to be a +8, -6, 2, and 4. Da 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 da. Yay! We have a whole 45 seconds left also. Wow. Hey, guess what, everybody? Do you think this is something that you're going to need to practice at all? Do you think it's important to do your homework for this? Nah. Carson's like, Wojcik, I got this in the bag. Notice we are multiplying again. Some of you were a little rusty on that. That was your homework from Monday. Make sure you do that. You should have had that done already to make this easier. Homework is important. That's your practice. Please, 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 please complete these over the weekend. You've got identity practice, inverse practice, and then solving matrix equation practice. Have the best day ever. Hang on.